So the skill is called implicit differentiation. And first we need to look at what an implicit equation or an implicitly stated equation is. So we're going to start with what explicit is. Somebody give me an example of a simple equation like of a function or something like that. Nice. So y equals? Very good. That's explicit. Okay. What would be another one? Cubic? Rational. Lots of the functions that we have dealt with would count as explicit. And we never talked about them as explicit because we never had a reason to, because we always work with functions in this form. We never had a reason to worry about, hey, there's a totally different kind. All the functions we've worked with so far are either in this form or could be put in this form. And at this point, you don't even know what I'm talking about because that just looks like every function just looks like that to us because this is my point, is that's all we've worked with so far. It's really all we've seen. Implicit. So if we compare that to implicit, then we'll see the difference in why all those other functions, all the functions we've worked with so far are explicit and what is the difference between explicit and implicit. So the first one, I'm curious if you would recognize it. Anybody know what that is? Mason? Very nice. It's circle. And maybe it's not clear yet. You have seen those before, obviously. Briefly in grade 10, maybe a little bit in grade 11 and MHF, but hardly. But if I show you another one, then you might start to see the difference in an implicit function or state is not a function because circle is not a function, right? I shouldn't say function. An implicitly stated equation of a curve or relationship and an explicit one. Does anybody want to point out what they notice, Max? Two variables on the same side. Yep. Anything else? Y term is squared. Yep. You might have to do some rearranging. So for example, what if I took this one and rearranged it for y? That's something that we do. In fact, we do equations like this. 3x minus 4y plus 10 equals 0. But that's a function. That's just a straight line. That's standard form. In fact, it's something you need to know for your test tomorrow. Right? That's just standard form of an equation. Or a more simple one, x plus y equals 5. That's a one we explore starting in grade 9. Max? Could you factor out 5y? Yeah, you could. Now, what would that do for us? That's a randomly made up question. So the fact that you can factor it or can't factor it doesn't really have anything to do with it, but you certainly could. What would that do for us? I'm not sure it would really do anything. So if, as an example, in the context of what we're talking about here, I'm going to move the x squared over, so I get y squared equals 25 minus x squared. And then what would I have to do to solve for y? I'd have to take the square root of both sides. So what's useful in what you do in grade 11 with, and then we look at a little bit of MHF, with the square root function and with taking the inverse of a function, is when I rearrange a circle, I have to do plus or minus, because I've taken the square root of something that was originally squared. And that is different from the square root function, which by definition is only the positive square root, right? So that's what makes it a function versus taking the inverse of a parabola, which has the plus and minus and isn't a function. And then we do the whole thing where we restrict the domain and blah, 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 that whole complicated mess, right? Okay. So part of the difference, I've sort of already commented on this. What kind of a circle is that? Well, it's the it's a perfect circle, and the radius. Does anybody remember or want to guess what the radius is? It's 5, right? It's the square root. So if I drew a circle, oh, that is a perfect circle, and this would be 5. And this would be 5, and this would be -5, and this would be -5. Okay, so that's what it looks like. So what is important about that circle? I've kind of mentioned it. Does anybody know what I'm talking about here? The fact that it's not a function. Is anybody thinking that? Okay, and this is sort of a sidetrack, but the positive version of the rearranging would be the top half of this circle, and the negative version would be the bottom half of the circle, right? So you would need two functions. If you're using function notation, you would need two functions to draw the entire circle, or we can have it implicitly stated. In case this is on your mind, technically speaking, these are relations that are implicitly stated because they're not solved for y. They can't be written in function notation. But to me, they're just not rearranged in the right form. Those aren't the kinds that we're interested in. These two and others like it are the kinds of functions that we're interested in, that we're really talking about when we're talking about implicit curves or implicitly stated curves, are ones where you cannot solve properly for y, and they are often, not always, I'm not going to say always, but very often are not functions. Okay? We have an idea of what an implicit and what an explicit curve is and what implicit means. So for example, on a test it might say find each implicit, or use implicit differentiation on each of the following, that we would know what that means. Oh, it's going to be one of these types. Okay. Oh, before we move on, just a note. This is kind of a notation thing or kind of a terminology thing, and I mentioned this the other day, but it'll have a little bit more relevance or context today. The derivative of y. What's the derivative of x? In what we've done so far. This is a tricky question that's actually easy and has an easy answer. In other words, if on the test you had to find the derivative of that, what would it be? 1. Thank you. So the derivative would just be 1. Or can I move this so it's going to be out of the way? Okay. So what's the derivative of y? Well, here's the trick. And we haven't talked about this yet. And we're only going to start looking at it a little bit right now. But when you take a derivative, you actually have to take a derivative with respect to something. So the derivative of x with respect to x is 1. So far, we're always taking the derivative with respect to x. The only time we saw something a little bit different was when we were using the chain rule and we did the derivative of with respect to u and respect to v, and then the du and the dv were on the bottom, right? So we actually have to take a derivative with respect to a particular variable. It's just usually x. So the derivative of y, as long as we're doing it with respect to x, that's what we say. is dy by dx. That's what it actually is. And so in the past, y was always by itself. So when I took the derivative, it became dy by dx. Like, we probably thought that was just a notation. This is just what we call it, but actually there's a little bit more to it, as there usually is. As our mathematical world grows, we learn there's actually more of a reason than we originally knew. So that's going to be important in what we do next. Okay, come back. Well, maybe come back and touch on that, or you can come back and think about that after we do a little question here. So here we go. Let's do some implicit differentiation, and we're going to leave an implicit form. What does that mean? We'll see that once we've done it in a moment. Yes? That's right. If you were taking it with respect, if you were taking the derivative with respect to y, you would kind of do the whole thing except for the y's instead of the x's. Yeah. So we notice that this is not this is in the form. This is the same circle we were looking at before. This is in the same form where y is not isolated for. And even if I did isolate for y, how would I take the derivative of plus minus? Well, you can't, right? You would have to do two separate cases or something, like, as I said, two separate functions. So it wouldn't make any sense. So that's why that's one of the reasons why we have implicit differentiation. So what's the derivative of 2x, this part, or x squared? There's your answer. This part hasn't changed, it's 2x. Here's the new part. Now I do the same thing, where I take the exponent and I bring it out front, and I have the same thing, and I subtract the exponent by 1, so it's 2y to the 1. But then, just like the chain rule or the power of a function rule, I do the derivative of what's inside, except what's inside is just y, but we just discussed this. What's the derivative of y with respect to x? It's dy by dx. So I'm still taking the derivative of that term in the normal sense that we've been doing these things, but then I'm also adding, whenever I have a y, the derivative of y itself is dy by dx. Whereas the derivative of x was 1, so we didn't worry about it. Make sense? And what's the derivative of 25? This is something we need to know. 0, thank you. And now we're going to put this back in implicit form, which just means solve for dy by dx. So I'll move the 2x over, and I get 2y. I should move that. It looks like y prime. It's y to the 1. 2y dy by dx equals negative 2x. And then divide both sides by 2y. And I get dy by dx equals negative 2x over 2y, which is just negative x over y. That's the derivative with respect to x in implicit form of the circle. So let's get that one little new step where we've got the dy by dx in an odd place. And I guess, to me, that's kind of what you're getting used to today. Okay? We okay with this? Okay, so I'm going to ask you a question. It might be a bit of a hard question, so I'm going to ask you to turn and talk to somebody that you're close to try to talk about this, and I'm going to give you a minute or two to think about it and talk about it. Here's the question. Why does the derivative have an x and a y in it? And I don't just mean algebraically y. I mean, like, think about a derivative. Why does it have x and y? Think about the function, sketch it, draw it, something like that. Okay? Turn and talk to somebody close to you and see if you can think through this at all. these two variables, but I think it helps to think about x and y in terms of the graphing and stuff that we've done. So, what kinds of things do we do from the day of the problem solving? Okay, good. Think about that. So that's like algebraically, that's why it happens. But then there's what I'm trying to tell you is there's a deeper sort of reason in the outcome. Why they both need to be there. Where? Where would it be the same? Okay, yeah, so, yeah, absolutely. So give me an example. That's what we call the general derivative. What if you wanted a specific? Sure. Pardon me. Okay, we're on to something here, folks. One thing I said, and this is interesting from a teacher's perspective. I've had a lot longer to work with this stuff than you have and really reflect on it. But the graph is so often important. Why do we have a whole course on functions where we talk about graphing? And I've known people who hate graphing. They're like, oh, I like math, but I don't like graphing. And it's like, oh my gosh, graphing is such an important part of math. We think about them as separate things. Algebra here, graphing here. They're not. The graph is supposed to inform us on the behavior of the function and why the algebra works the way it does and help us with our understanding. So I said, why don't you try drawing it? Had some great conversations. So over here, they were saying, and a lot of people got this, that the derivative is like the slope of the tangent. So this would be the general derivative. And I said, derivative where? And they said, anywhere. And I said, give me an example. So somebody give me, and they said, well, like you'd get an x. So give me an x. 2. I like that one because our original curve only went to 5. So if you said 10, I'd be like, ooh, that's not on our curve. Good. So what happened? What's going to happen now? John, what's going to happen when I go to 2? Yeah. But what do I get in my answer for my slope? Mason? That is kind of true. X over Y looks like a ratio. Yep. Anybody else want to help? It seemed like everybody was right on the edge of it. Max? How do I know which tangent line I want? Do I want this one or do I want that one? So I need Y to figure out which point. Because again, remember I said we're often looking at something that's not a function. And when we don't have a function, picking an X isn't enough. Okay, you picked X. X on which part of the curve? So we need that Y in there as well to tell us which actual point on the function are you at. Are you, okay, we're at X equals 2, but are we up here? And look at the slope up there. It's negative. And we're down here and look at the slope down here. It's positive. And this comes back to the idea that it's kind of like a ratio because this is negative. So if the Y value is negative, it's going to make the whole slope positive, or if the right, like it's all going to work out. But anyway, very interesting. So think about that. This is important. If you ever have a problem to solve with an implicit curve, you got to have X and Y to plug in to solve for your slope of the tangent because you're probably looking at something that's not a function. Okay, that's just a little thinking exercise, kind of interesting. Let's move on and do some more actual work with this stuff. And then down the road, when you're solving problems, if it's an implicitly stated curve, you got to remember there may be extra information you need that's different from anything you've done in grade 9 and up, where you needed X and you plug it in, solve for Y. That may not be true anymore. You may need more information. Okay, so what am I going to do here? What's the derivative of 4x cubed? 12x squared. And remember, because this is like sort of like polynomial form. This actually is a polynomial, but it's a polynomial that's in more than one variable, which you can have, but we don't explore very much in high school math. So it's still in kind of like polynomial form. So I could just take the derivative of the parts individually, right? I don't have to worry about using the product rule, the quotient rule, or anything like that. But don't take for granted that that's a definition that we looked at, that I can take the derivative of each part and just add those. What's going to be the derivative of the next part? Here's the tricky part. Well, I'm going to bring the 2 down and multiply it by -2, so I get -4. And y, and then dy by dx. And instead of equals 7x, what's the derivative of 7x? It's 7. And now I have to do a little bit of algebra, which hopefully is the easy part. You don't want to make a mistake here. Do all the hard stuff right, and then screw up this part. 7 minus 12x squared, and divide both sides by -4y. And I've solved for dy by dx. And then I'm sure people have all kinds of questions. Well, what do we do now? Like, do I split that, or do I try to isolate the x and y? No, that depends on, again, context, as I've always said. What are you doing next? Depends on what form you would want your final outcome in. Just because it's a nice thing to remember, one thing I might do is I might take the negative sign and multiply the top by -1, which would give me 12x squared minus 7 over 4y squared. It's not necessarily something you have to do, but just recognizing that that's the same thing, right? And that can be useful of how to deal with negatives inside a binomial or something like that, or inside an expression, how to deal with that. Yes? Yes, thank you. Where'd the squared come from? Absolutely, yeah. Okay, try another one. Why don't you give this one a shot? Okay, when you look at this first part, what do you see? John? And when so this is a little bit tricky actually. your intuition may have failed you a little bit on this one. Isn't that the product rule? We're taking the derivative of something times something. So every other example that we've already done didn't have an x times a y. That qualifies as the product rule. So which order should we do this in? Let's do it where p is like 2x and q is like y squared. So p prime is 2 and q prime is 2y dy by dx. So this ends up being the derivative of the first, which is 2, times the second, which is y squared, plus the derivative of the second, which is 2y dy by dx, times the first, which is 2x. And then, very strange that it was 2 terms and now it's become 3 terms. What's the derivative of y cubed? 3y squared dy by dx. Derivative of 4 is 0. Does that make sense? Everybody see why we did that product rule? So this part came from the derivative of that first term. What do you think we have to do now? We got to isolate for dy by dx. How are we going to do that? We have 2 of them. Okay, let's start. Well, let me fix that. So this is going to be 4xy dy by dx plus 3y squared dy by dx equals negative 2y squared. What do I do? Very nice. Is that something I can do? Yeah, of course it is. Yep, absolutely. Factor out the dy by dx. Elif, did you have a question or were you going to add something? This is where we were taking, I think you're talking about right here. This is where we were taking the derivative of that. Yeah. So this was 2 times 2 and x times x. Or x times y, sorry. X times y. And this 2y squared came over to the other side, right? Okay. Good. And then hopefully this last part is obvious. Dy by dx equals negative 2y squared over 4xy plus 3y squared. Okay? Okay, again, I think you can try the first line of this one. You might do a little bit better because you recognize the product rule in there again. Yes, Emma? I think, like I said, that depends on what you're doing next. I don't think you're going to get it to simplify enough where it's going to like really neaten up. And from the last unit, we like to have one fraction because then if I set it equal to 0, I know that the top is 0. Whereas if I split it into 2 fractions, yeah, I can simplify each individual fraction, but I can't solve for 0 as easily. So I think for us, that's the form we're going to leave it in for now. But absolutely down the road, that you're right. There's other ways we could do it. It's just if we would have a reason to do it. All right, give that one a try. Nice. I see a lot of people writing the P and the Q off to the side. This is a great, I like how you're using that strategy on your own. I mean, I did use it for the first one, but normally I might not. But it does help you focus your thinking. So if you want to do that for now, absolutely use that strategy. Product rule. What's my product that I'm taking the derivative of? 3x squared times y to the 4th. So that's your P and your Q. Probably wouldn't usually write that 0 for the 1, but for now, it's fine. What's my derivative on the right-hand side here? Does anybody have that? Am I good so far? Is that all right? I think I'm good. I put the negative here. But that is something that, like, which one's negative? The 3x squared or the y to the 4th? I mean, not the whole term is negative. You just got to make sure you keep track of it somewhere. In fact, I could just do subtract and then, like, take the derivative, like, leave the negative sign out front. You know what I mean? But anyway, yeah. Yes? Do we put dy over the x? Does anybody else think we probably should do that? I agree. Yes, we should. Definitely. Very good. All right. What are we going to do? Isolate dy by dx. So this is just like back in grade 10 where you're sort of solving by factoring kind of thing, right? Except we're not solving for 0, but we're isolating. So, negative 6x y to the 4th equals, I'm going to move the other dy by dx term over, and I'm going to simplify it a little bit. So it's going to be plus, because the 3 times the 4, I can do 12x squared y cubed dy by dx. Are we good? Questions? Any questions? All right. So here we go. What if we wanted to actually do something with this? Find the equation of the normal line to the curve. A while ago, there was an optional question in the homework that talked about a normal line, and I said you'd have to refer to the glossary. Did anybody do that? Has anybody ever heard of a normal line or read about that? And do you remember what it said? Very nice. Well said. Did you have that written down, or is that from memory? Yeah, you did it, but you remember it. That's fantastic. So a normal, if I have a function, that one looks cubic, doesn't matter, and I pick a point, the normal to the function at that point, okay, is as if I had a tangent line that goes through that point at that point, right? And like tangent to the curve. And then I take the line that's perpendicular to that, but passes through the same point. So perpendicular to the tangent line, but passes through that point. That's what we call a normal. So before it was optional. Now that we've done it together, it's something you need to know. I wouldn't be surprised if it showed up on a test, not the one tomorrow, but a test somewhere where you have to, where it'll be like, find the normal, okay? So what are we going to do first? Well, we need the slope of the tangent so we can find what's perpendicular to that. Oh, this is perfect. We haven't done I haven't done an example with you of a line that's perpendicular. But if it's on, but I have said it could be on the test, and I believe it was in the homework, and it's something you should know. But I know that because we haven't done it since grade 9 and 10, people forget how to take a slope and make it perpendicular. So now we're going to do it. So here's your chance to really get this. So 5y to the fourth. If you hadn't already done it, you're being saved. If it's on the test. Product rule. X squared times y. So plus 2. The derivative of the first is 2x times the second. Plus the derivative of the second, which is just dy by dx, times the first, which is x squared. And then I've got another term, minus, so the derivative of 2x squared is 4x equals 0. I got 4 terms. 2 of them have dy by dx and 2 of them don't. Okay, see if you can finish isolating that for dy by dx. Okay, now what are we going to do? So here's where like problem solving comes in, and what are we ultimately trying to find? We're trying to find a normal, which is an equation of a line. What do we need to find an equation of a line? 2 points would help, but we don't have 2 points, we only have 1. What's the point? It's the point that's given. So I could also use point and slope. What's the slope of the normal? Perpendicular to the tangent. So if I find the slope of the tangent, I can find what's perpendicular to that, and I can plug those in to point slope formula and find the equation of the line. So, there's the big reveal. Hopefully you got that. 4x minus 2xy over 5y to the fourth plus x squared. So then dy by dx at the point 2, 1, that was the point that was given. And we just sub in. Eight minus 4 is 4 on top. And that's 5 plus 4 on the bottom, so 9 on the bottom. So slope of the tangent is 4 over 9. Why did I write a D? 9. And slope perpendicular to that, or slope of the normal, is, what's perpendicular? Thank you. So that's the part right there that you can do all this amazing calculus, taking derivatives, implicit differentiation, all this stuff. And then people forget from grade 9 what it means to be a perpendicular slope. Right? Take the reciprocal and change the sign. The negative reciprocal, we call that. So now I'm finding the equation of a line with the slope of negative 9 over 4 at the point that was given 2, 1. On the test, it says, I'm talking about the test tomorrow, and then also in the test in the future, find the equation in standard form. So the learning goal didn't have that, and I wonder if some people have been doing it that way and some people haven't, but make sure you understand standard form. I'm just going to go over that. In fact, when we took up that learning goal, I'm wondering if we covered it. Okay, so I'm going to multiply both sides by 4. I get 4y minus 4 equals negative 9x plus 18. And I'm going to move everything to the left. So I get 9x plus 4y minus 22 equals 0. When I was in high school, I was taught that standard form required the coefficient of the x term to be positive. That's not really true. That's like a made-up math class rule so that your answer perfectly matches the answer in the back of the book. At this stage, each and every one of you, if you had the negative signs reversed, you had negative 9x minus 4y plus 22 equals 0, you'd look in the back of the book and be like, yeah, mine's the same. Like you could see it. But in grade 9, they can't see that. They'd be like, oh, shoot, I got it wrong. So we make up a definition to force them to do it exactly the same way just for checking their answers. So you don't have to worry about that. But my point is, but standard form for us does mean integers. So these can't be fractions. So be careful of that. Okay, they can't be fractions. Even that definition, honestly, is debatable. But what I want you to do is make these integers, make sure we clear all fractions, make it nice and simple. That's going to be the definition we go with. Okay? One more. I'm going to let you try this one from start to finish on your own. Similar to the last one, just easier. Very good. Good job, folks. All right. I'll put mine up, but otherwise we're done here, I think.